Hi, Dr. Charles Martin here with Calculation Consulting. Thanks for stopping by my channel. Today I'd like to talk to you about what I call PaperWare, or how to read and use a scientific paper in your work. I hope you enjoy the video, and please like and subscribe if you do. Now, a lot of you may remember a concept called vaporware. In the old days when software engineering was a thing, before AI was taking over the world, people used to write software and they would make all these claims about the features of software we're going to have. Oh, we're going to do this, we're going to do this, we're going to do this, and this will all come out in 2 years. We called it vaporware because there was all this talk that people said all these features of software we're going to have, and they never produced anything. Well, now AI is eating the world, and I like to use a term called paperware. And by paperware, I mean when somebody reads a scientific paper, in particular a paper on deep learning, and they think, okay, this paper is going to solve all my problems. And what I want to really talk about is, how do you read a scientific paper? How do you take advantage of the recent advances going on in deep learning? Now, this is a really complicated problem because, in software engineering, when you want to build something, you just figure out what you want to build and you build it. Maybe you don't have time to add all the features in, but in principle, you could have added them in. In deep learning, it's very, very different. You may want to do something and you have no idea how to do it. And you're not going to be able to just sit down and hack it out. You're going to have to go and find some other implementation, some reference implementation, and try to get that thing working in production. And it's really challenging because unless you're working in a very large R&D lab, which is doing research in deep learning, you're going to have to rely upon other people and the other work that they've done, the things that they've been willing to open source. And not everything works the way you think it would. So let me give you an example. Recently, I was looking at an article that came out. It was actually a University of Chicago study. And they claim that they're able to generate fake Yelp reviews. We can just generate fake Yelp reviews using deep learning. Well, that's actually a pretty hard task. Deep learning is pretty good at generating fake images, and it's pretty good at generating music. But generating text and doing textual understanding has been much, much harder. Tools like autoencoders and GANs just haven't worked the way on text as well as they do on images. So when I read this paper on, wow, we can generate fake reviews and they look real, well, first thing I thought is, well, okay, where's the code? Show me the code. Well, I went to GitHub. So I go to GitHub and I look at the researchers who have done the work, and I search around. I don't see anything. I don't see any GitHub repo at all for any of them. I go, okay, what's going on here? Then I go and I email the guy. Look, I'm a University of Chicago guy. You're a University of Chicago guy. What's going on? He goes, well, we haven't released the code yet. I go, well, if you haven't released the code, why did you publish? I'm just of the opinion that if there's no code and there's no data, there's no science. We went through this when I was doing research in quantum chemistry. It was the same thing. You could run a quantum chemistry calculation, you could claim you've been able to solve the Schrodinger equation and make these predictions on molecules, but it was all numerical. We had to see the code. If you didn't show the code, it was very, very hard for someone to re-implement what somebody else has done. They're all little, it's just very, very hard to do. And in particular with today's technology, with TensorFlow, with Keras, with PyTorch, with all the deep learning frameworks that are out there, and they're open source and they're pretty stable. You would expect that when you read a paper, first thing you should do, even before I read the paper, is I look inside the paper. Is there a reference to a GitHub repo? If there's not a reference to a GitHub repo, start to wonder, maybe this isn't real, okay? Well, if there's not a reference to a GitHub repo, I will go on GitHub and I'll look up all the researchers and look at their personal repos and see if there's something there. Every once in a while, you do find something. In fact, a while ago, I was reading a paper on dark knowledge by Lee Kun, and a friend of mine and I were trying to reproduce, and we're like, this just doesn't make sense. We were able to track down the repo, and we found a bug in the code. Of course, this points something out which is very important. Just because someone's name is on a paper doesn't mean that they did the work. They may have hired a postdoc, or maybe they had a summer intern. Maybe they were publishing the paper for a proceedings of a conference or something like this. And, the work, maybe it's good, maybe it isn't. No, what research, especially when you're a very high-level researcher running a lab, do you really think they're reading all the code that everyone produces? Not going to happen. So this is really important when you're looking at things in deep learning. Now, so what I try to do is when I find a paper, I look for the GitHub repo. If it's not in the paper, I go and I try to find in GitHub, can I find what the researchers have been doing? Then I want to find the code. If the code is there data? Is the data there? Did they modify the data? What did they do? And I try to run it myself. Now, even with all of that said and done, you may find that you run the calculations and you just don't get the same results. That's rather puzzling. Of course, what's happening is that there are lots of little quirks that go into getting a deep learning calculation running. For example, you have to have the right initial conditions. You have to set the learning rates properly. You have to have the right regularization. All of these little knobs have to be twisted and tuned to the right exact operating point. And you've got to be careful. Someone might publish a paper where they've run 100 calculations, and maybe 3 or 4 of them did well because they had random initial starting conditions. And they just published the ones where they had the random initial starting conditions. They don't tell you about the other 95 examples that never worked. It doesn't sound like science, but it's just the way it is. And it was no different than doing quantum chemistry or doing physical chemistry in the laboratory. I saw this stuff all the time. So the reality is that you've got to be careful. Nevertheless, there is a lot of really great stuff out there. For example, I was recently looking at a paper on causal variational autoencoders. Really interesting stuff. Ways of mixing, doing causal inference with deep learning and Bayesian neural networks. Very interesting. There's code. It's well written. It's by Welling and Welling's group. Very famous guys in the field. Now the question is, can I adapt this code to use it? It should be open source for one. If it's not open source, you have a problem. Back in the old days, I worked on SVMs 10 years ago or more, but there were no good open source SVMs. So it caused a problem for us. I was at eBay and we were using these structural SVMs. It wasn't that they didn't work; they weren't open source. So you want to make sure you have a license to use the thing. Then when you implement it, you want to be able to implement the code on. You want to make sure you know how to implement it on different kinds of data sets, and that's a challenge. And when you read a scientific paper, there's usually some context. These guys already know what the data sets are. They're familiar with the common data sets in the field. And so you have to really go to some work to get some sample data sets and make sure you can run it on the variety of different kinds of inputs that you are going to want in your business, in your company for your clients. Once you've done that, you can put a tool together. And you have that tool, and that tool can go into your toolbox. And, of course, you've got to maintain it. But it's a great way to really try to take advantage of these papers. And to read them is to find, you want to translate the paper into a tool, just a command line tool. It runs in Unix that you can put in your toolbox and you can use for doing something like a back of the envelope calculation when the time arises. Now, as I've said, even when you do this, you've got to get some experience with the tool and just play around with it a bit. Many years ago, there was a lot of interest in transductive learning, semi-supervised learning. And there were a lot of work on semi-supervised SVMs and transductive SVMs. And in fact, I even have a book. There was an old book. There was a whole research book on this topic. The question is, whatever happened to this stuff? Why didn't it go anywhere? Why is deep learning now taking over the world? Well, it turns out in the semi-supervised world, there was a little adjustable parameter, the R parameter, the fraction of the positive and negative examples. And if you didn't set that parameter exactly, you would get the wrong result. And the problem is, in the academic literature, everybody knew this. They knew that we were just trying to solve this semi-supervised problem. All the problems have been posed, and the inputs are set. Now, when you go into the real world, you might say, gee, this is a really great method. It works really well. But, I don't actually know how many of my examples are positive and how many are negative. I don't know the fraction. Heck, if I knew the fraction, I'd probably solve the whole problem. So the fact that the academics have certain baselines that they're trying to hit doesn't mean, and the fact that the method works doesn't mean that's going to work in production for you. You've really got to make the effort to scratch your head and ask, what assumptions are these guys making? What assumptions are in the paper that about the data sets that they're using? And do those assumptions match what we're going to be doing in production? But generally speaking, if you can sort this out and you can get the thing to work, there are a great number of tools out there. The last thing to remember is that just because something is new doesn't mean it's better. There really are a lot of different roads that go to Rome, as they say. There are a lot of different methods for solving the same problem. And just because you have a fancier method or a deep learning method doesn't mean it's going to work better. So it's good to have, once you have the paper and you've read it, to go back and look, what were the things that were done in the past? And does this thing actually work systematically better? And then you've got a toolbox, you've got a screw, it's like having a screwdriver with 3 or 4 different knobs you can twist, and you can try them out. Anyway, I hope this has been helpful. This is the way I look about when I'm reading a paper and trying to add tools to my toolbox in deep learning. And I want to thank you again for coming to my channel. Please like and subscribe if you enjoy these videos, and feel free to send me suggestions of other topics to discuss. Once again, I'm Charles Martin with Calculation Consulting. Thanks again.